Okay, we're going to go ahead and talk about the disk method. So we're going to do that through looking at an example. So here we have, it says find the volume of the figure formed by revolving the region bounded by y equals x squared, y equals 0, and x equals 2 about the x-axis. So that might seem a little strange right now for those of you that haven't done a problem like this before. But what we're going to do here is the first thing is I'm going to look at this region. Okay, so I have y equals x squared. Y equals 0 is just the x-axis right here. Okay, so this is the graph y equals x squared. Y equals 0 is just the x-axis, and then the line x equals 2 is a vertical line. Let's say it's right here. X equals 2. So the region that I'm talking about is this region right in here. Okay, this region right in here. And what it's asking us to do is to take that region and rotate it about the x-axis. So again, we're taking this, and it's very difficult to visualize. This region here, it's attached to the x-axis right here, and it's just kind of going to rotate all the way around, kind of come out of the board, and then go back around behind the board, and wherever it goes, it's creating this three-dimensional figure. To kind of get an idea of how it looks like, what you can do is you can draw a reflection of your region in the line of rotation. So the line of rotation here is the x-axis. So I'm going to go ahead and draw kind of a reflection of this region, as best I can. Okay, and what I want us to think about is, what would the cross-sections of this region be? What I mean by a cross-section is, if we were to kind of, take a slice out of this and pull it out from here, okay, and look at it, what would that cross-section look like? And the idea that you have to keep in mind is, at any point along this line, okay, let's just pick this point right here, for instance, that is a certain distance away from the x-axis, which happens to be the line of rotation here. And as this graph rotates around, it's going to remain the same distance away all the way around up until it hits where it started from. Okay? So the idea that if you kind of keep something and it's almost like there's a string attached to this and it goes all the way around, what it's forming is a circle. So this has circular cross-sections. Okay? So I'm just going to draw a few sample cross-sections here. Try and give it a three-dimensional feel, because that's the thing, that's why it makes it very difficult to draw this, is because this is supposed to be three-dimensional, but not looking so good here. There definitely are places on the internet that use computer programs to make a nice three-dimensional image, and it makes it easier to see what's going on. But in terms of visualizing what this looks like, to me I would say this kind of looks like a Hershey Kiss turned on its side. With this being the top of the Hershey Kiss and this part being the bottom, that's kind of what this looks like once it's made into a three-dimensional figure. Okay? So, kind of the thought process here that we're going to do is think, okay, well, all of these circles right here, okay, are infinitely small. They're all infinitely small. Okay? And what the integral is basically going to do here is add up these infinitely many small circles, basically. The width of these circles is essentially 0, okay, or approaching 0, I guess, and so the integral is going to add all of these up. You could originally, like we originally started when we did area under a curve, we used the idea of rectangles to approximate. Well, you could actually make kind of like cylinders like that, and that's a horrible drawing of the cylinder, I apologize, to kind of approximate the area under here, and I'm going to kind of refer back to that in a minute when we look at our integral, as what part of that integral represents. Okay? So anyways, the key is the cross-sections are going to be circles. So what we're going to use, whenever you're rotating around a line, you're always going to use a equals pi r squared, okay, because all of these cross-sections are circles. Okay? And I know in this example I'm going to take a little bit longer. On the other ones, I'll have assumed you saw this one so that we can move a little bit quicker. Now, what I recommend to do on all of these problems is to draw your radius, because what you want to do here, you want to find, okay, a equals pi r squared, it's like, what am I talking about? I'm talking about the area of these circles right here, but you notice how these circles change in area depending on where x is. In this particular figure right here, as x is real close to 0, that radius of those circles is very small, so the area of the circles is small. But as I get further to the right, the radius of the circle gets larger, and so does its area. So what we need to do is we need to figure, okay, well, what is the radius of this circle? And it's not just a number like 5 or 7. Every once in a while we'll have something like that, but in this case it's not, because the radius changes. So the way I recommend I can't recommend this enough for your radius, is to draw it out. Okay, and the way you can draw it out is to start somewhere on your line of rotation, so which is the x-axis in this case, that's what we're rotating about, and to draw my radius to the outer edge of my region. Now I'm not going to draw it down because that was just a reflection of my region. You know, eventually I'm not even going to draw the reflection. I'm going to draw up in this case, right here, okay? That is my radius, okay? Now I chose that as, you know, that's where I chose to draw it from. I could have chosen right here. I could have chosen anywhere. It doesn't matter. Just draw one sample radius, okay? And that's all that matters right now. So the radius in this case is the distance from the x-axis up to the graph. So this graph y equals x squared determines the height of the radius at various values of x. So let's just say I wanted to know what was the radius at x equals 1. I would plug 1 in for x in there, and I would get 1. Okay, if I wanted to know what is the radius at x equals 2, I would plug 2 in, and the radius at 2 is equal to 4, and so forth and so on. But in general, at any given x value, the radius is just x squared. And here's just kind of a general rule of thumb that's always going to work. If you draw your radius correctly, your radius is always the top equation it hits. In this case, the top equation it hits right here, okay, that I'm pointing to is y equals x squared minus the bottom equation it hits, which in this case is just y equals 0. So x squared minus 0 is just x squared. So what I'm going to do is I'm going to take x squared and I'm going to plug it in where I see r. Okay? So key to these problems here is finding the radius. That is an absolute key to this. Okay? And I'm going to go ahead and I'm going to just simplify this. So that's pi times x to the 4th. So this pi x to the 4th represents the area of these circles. And again, we just talked about, you know, at various values of x the area changes. That's why there's an x in that area, because it changes depending on where x is. So if we can add all of those areas of the circle up, we've got what the volume of this figure would be. Okay? So the way we're going to add all those circles up is by integrating. And we're going to integrate. So when I do my integral, I always like to put pi out front because it's a constant. We can put that outside the integral. And x to the 4th dx inside. Okay? And this is where I was going to refer back. This dx right here is really representative of the width of your circles. Which again, I said kind of the width of this circle right here is 0. But you know, back in the day, you know, when they were just approximating this using cylinders, those cylinders would have certain widths. And then the more and more of these cylinders you use, the widths would get smaller and smaller, and eventually use infinitely many, and that's what leads us to an integral. But that dx right there is just representing the width of those cylinders. Okay? Or I guess it might be the height of the cylinder in that case. But anyways, one more thing we need to do here, we need to put limits on this integral right here. So in this case, you know, these circles are being added up from left to right. They're stacked from left to right, so we're going to integrate from 0 all the way to 2. So from x equals 0 to 2 is where integral is going to take place. Now it's just a matter of evaluating it. So it equals pi times antiderivative of x to the 4th is x to the 5th over 5 from 0 to 2. Plug 2 in for x, becomes pi times 2 to the 5th over 5, which I could leave it like that, you know, and then I'd minus plug in the 0, but it's just going to be 0. And 2 to the 5th is, oh my goodness, what was that, 32? So that's going to be 32 pi over 5. So just to make sure what this number represents, this 32 pi over 5 represents the volume of this figure right here. That is the volume of that figure.